Good morning. Today we will discuss about the transient stability of the power system. In the last class, we have discussed the steady state stability or small signal stability. So, depending on the sigma, we have derived that we can find whether the system is stable or unstable, depending on the my synchronizing power coefficient. In transient stability, what is the transient stability? So in first class only we have discussed about this, we have defined. Again I will define here. So transient stability is the ability of the power system to remain stable under large disturbances. Here as I said, the large disturbances. The large disturbances may such as short circuits, faults and line outages, sudden load changes and sudden generator changes. So what is the need to study the transient stability? So the evaluation of the transient stability is required in two ways. One is for offline and another is online. Offline studies is useful for planning, designing, etc. And whereas online studies will be useful for load management, emergency control, security assessment. So in small signal stability or steady state stability, it depends on only the initial operating point. But whereas transient stability depends on many factors. It is initial operating point, it depends on initial operating point, it depends on the type of the fault, it depends upon the location of the fault, it depends on the duration of the fault. Also it depends on the duration of the fault. So for any power system, just for example, for power system, I cannot, transient stability, I cannot give a general statement. So how to give the system to be stable? Like for a three-phase fault at bus 6 occurred for 300 milliseconds. So I need to specify each and everything. The type of the fault, as I specified, it is three-phase fault, and the location I have mentioned it is at bus 6, and the duration which I mentioned it is 300 milliseconds. It cannot, generalized statement cannot work, cannot be stated associated with the transient stability. Whereas in small signal stability, you can tell that. So depending upon the synchronizing power coefficient, if it is a positive, we can say the system is stable, but that will not work with the transient stability. So two aspects for the transient stability will be considered. So one is, given a fault, can we find out whether the system is stable or unstable? For a given fault, we can find out whether the system is stable or unstable. Then actual solution of the swing equation. Here we will plot delta varies with the time. Plot of delta varies with the time. That means delta versus time. So here our interest is, so I am not interested in finding of the swing equation. I am interested when the fault occurs, I need to find whether the system is stable or unstable. So I am interested in first one. I am not interested in second one, and it is beyond the scope of the syllabus also. So for this we will study, for given a fault, whether the fault may be of any type. For that, when the fault occurs, whether the system is unstable or unstable. It may be pre-fault, post-fault, or during the fault. Now, the main thing that the transient stability analysis deals with the actual solution of the non-linear differential equation, because our swing equation sin delta is a non-linear function describing the dynamics of the machine and their controls, and interfacing with the algebraic equation describing the interconnection through the transmission network. So the sentence is too long, I will explain this. Now, in your system, you have two types of equation. The first equation is differential equation. So this first equation is differential equation, and this differential equation already we have studied associated with the rotor dynamics. So which is represented by the second order differential equations. Now in a power system, there are so many controllers associated with the generators. For example, you may have simple AVR systems, you may have governor control, and you may have power system stabilizers. These are all various controllers associated with the generators, and which are modern generators is equipped with, and which are every modern generator is equipped with it. Now, how do you describe a controller? You can recollect from the control systems. Basically, a controller is described by its transfer function. Now, how we will define this transfer function? How we will relate the transfer function? Now, the transfer function relates a differential relationship between input and output. So, given the transfer function, you can translate between the input and output. Now, I have a differential equation not only for rotor but also for controller associated with the machines. So, I have a differential equation with the rotor and also with the controller. Now, to give you an ideal about the magnitude of the system, just say a single generator having two first order equations associated with a rotor, because second order differential equation is equal to the two first order differential equations. If you take the differential equation associated with the controller, a single generator minimum to minimum will have 8 differential equations. Now, imagine in your system, you have 50 generators. So, you will need to solve 400 differential equations. So, 400 differential equation you need to solve only if you are considering it is in 50 generators in the system. All of this to be solved with some numerical methods. Now, the algebraic equation describing their interconnections. So, their interconnections. So, this is nothing but the nodal equation of all the buses of the system. Now, the typical power system may have around 400 to 500 nodes in reality. Now, dear students, I want to understand the magnitude of the problem on hand. Now, you have a problem on your hand. So, you are required to solve simultaneously about 400 differential equations. So, all the 400 differential equations is to be solved. It is a complex problem. Now, how we need to assume and how we need to solve, we will see that. So, since the disturbance is large linearized analysis of the swing equation, which describes the rotor dynamics. The disturbance, initially it is a non-linear function, then we will consider that linear analysis by taking the part of the curve. Further, the fault may cause structural changes in the network because of the power angle curve prior to the fault, during the fault, and post fault may be different. This I will explain. Yes, this is a pre-drawn this. Now this is the power angle which is prior to the fault. The power angle curve, this is prior to the fault. That means before the occurrence of the fault. and this is the power angle curve during the fault. Then this is the power angle curve. It is after the fault occurrence or post fault. Now the network has been changed. When prior to the when the fault had occurred, the power angle curve have been this, and the post fault the power angle curve this. So prior fault the power angle curve it is. So the network has been changed, however the fault occurs in the system. So this is nothing but the structural change in the power system. So this what they had been given. Yes. Further, the fault may be cause structural changes in the network, because of which the power angle curve will be differ for the before or during or the post fault. Due to these reasons, this is very important, due to these reasons, a general stability criteria for transient stability cannot be established as it was done in the case of steady state stability. In case of steady state stability, what we will discuss is that if my synchronizing power coefficient dou delta by dou t, if it is greater than 0, I will say it is a power angle, I will say my system is stable, but it cannot be applied in transient stability. We cannot say generalized statement or generic statements in transient stability. So stability can be established for a given fault by the actual solution of the swing equation. Only the stability can be established for the transient for a given fault only by actual solution of the swing equation. Now, the time taken for the fault to be cleared is called the clearing time. Let us say in your system, as the fault occurred in some bus, so to clear that fault, it taken some milliseconds, just say 300 milliseconds. So that is the clearing time. So usually the fault is cleared in most of the cases by the circuit breakers. Now, if the fault is cleared fast enough, now whatever the fault occurred, if it is cleared fast enough, the probability of the system remaining stable after the clearance of the fault is more. That means it is when the fault is cleared fast, the disturbance is less. Once the fault is cleared fast, the probability of the system to be remaining stable is more chances after the clearance is more. If the fault persists for a longer time, no, it has been not cleared in predefined time. If it persists for a long time available, if the fault persists for a longer time available for clearing the fault before the system loses stability. That means if the fault persists for a larger time, so for clearing the fault before that system may lose its stability. If the fault still persists, the breakers open permanently. If the fault persists for a longer and longer time, the breakers open permanently. So since the most faults are transients in nature, the first recloser is in general successful. That means even for the first operation only, since the most faults are transients in nature, the first recloser is in general successful. Usually when the fault occurs in the system, there will be an equipment called the auto reclosers. When fault occurs, the breakers will open that automatically, and when the fault goes on reducing, after once the fault has been reduced or once the fault has been come to initial condition, now again the breaker closes itself, it is automatically. So since the when if it for two sequence of operation, if it does not work, then the breakers open permanently. Since the most faults are transients, the first recloser is in general successful. In only first recloser it will be successful. Hence transient stability has been greatly enhanced by the auto recloser breakers. This is important. For transient stability, we will hence transient stability has been enhanced by with the help of the equipments called the auto recloser breakers. If it is failed for two sequence of operations, then it is permanently opened. Usually in general, for the first sequence of operation only, it will be successful. Some of the assumptions made during the transient. However, we made the assumptions in the swing equation. Here also some assumptions are made in the transient studies. So the first assumption is that transmission line and synchronous machine resistances are neglected. Here transmission resistance and synchronous machine winding resistance are neglected. So this leads to pessimistic results, as resistance introduces a damping term in the swing equation, so which helps stability. That means he had been given, since resistance introduces a damping term in swing equation, that gives the pessimistic results. Here we require pessimistic results. If you get the optimistic result, again then it will be reverses the stability, again there is a problem, there is a danger. So here we will require pessimistic results. Then the effect of damper winding is neglected. That means damping term contributed by synchronous machine, damper winding is ignored. This also leads to the pessimistic results for the transient stability limit. Now, variations in the rotor speed are neglected. That means rotor speed is assumed to be synchronous. Synchronous means constant. In fact, it varies insignificantly during the course of the stability transient. But these variations in the synchronous speed will be neglected. And mechanical input to the machine is assumed. Mechanical input to the generator is assumed constant, which means that mechanical input to the machine is assumed to remain constant during the transients. That is, the regulating action of the generator loop is ignored. The governor control loop is neglected. This also leads to the pessimistic results. Now, the generator is modeled as constant voltage source beyond a transient reactance. So here there is no fluctuations in the generator. The generator is modeled as a constant voltage source here beyond a transient reactance, neglecting the voltage regulating action. Now, loads are modeled as constant admittances and absorbed into the bus admittance matrices. This means loads are modeled as constant admittances. This is reasonably accurate representation. Now, so why this all assumptions? What is the implication of this assumption? We need to study. So all these assumptions, vastly why we require these assumptions means it simplifies the equations. A digital computer program for transient stability analysis can be easily include more detailed generator modules and effect of the control. So first of all, why this assumption is to simplify the equation. a digital computer program for the transient stability can be easily included with more detailed generator models and effect of controls. So the discussion on which is beyond the scope of the present treatment. Now in next studies on the transient stability of an SMIB, single machine infinite bus system, and the power angle equation, and equal angle criterion we will discuss in the next class. So thank you. We will see the equal angle criterion, which is the most important topic, in the next class. Thank you.